Well, if you think about spiders again, then as we said, the exponential growth is not a realistic scenario, right? So what is a realistic scenario, and how does it work exactly? I'm going to tell you a story about this very beautiful spider. It's called a golden silk orb weaver. By the way, they are present in Singapore too, if you look around, especially at Sungai Buloh Nature Reserve. So it's a very large and very beautiful spider, and it is famous with making a very strong web. Right, so here you see a dress made of silk from a lot of the spiders. This web is so strong that among all materials known to the humankind, only Kevlar is stronger than this spider's web. And because of that, there were attempts to grow the spiders commercially, like they grow silkworms. But unfortunately, all these attempts fail, and the reason is because these spiders tend to eat each other if they are too close. Right? So which you can think of like modeling with a differential equation that the if you write a differential equation dy dt, then the growth rate of the spiders is proportional to the population, so which means that you must have some kind of some kind of a term proportional to the population. But at the same time, you must have a negative term proportional to the square of the population, because the square of the population is roughly the same as the number of pairs of spiders, right? So the more pairs of spiders, the higher is the chance that they meet and eat each other. So which means you will have to introduce some kind of maybe another coefficient. Let me write, I don't know, a y square. So you can think of it in these terms, or you can think of it in these terms. Of course, if you expand the brackets in the first version, you will get the other version. So this is called a logistic equation, and let us look at it again. So at the right hand side of the logistic equation, so notice that here we suppose that r is a positive number and k is also a positive number. So notice that if y is much smaller than k, then this term here is almost 0. So it's just a very small number. So 1 minus a very small number is still like 1, and which means that this whole thing disappears, and the rest is almost the exponential growth. But now if y is growing and is very large, so now if y is approximately equal to k, then now y over k is approximately 1, and then here we get 1 minus 1 is almost 0, so this is almost 0, and now the right hand side of our equation is almost 0, and we get almost no growth, which means that y is almost a constant. So and also you can see that both 0 and k are equilibrium solutions. And basically the on the plane yt, here is the line y equals k, and the right hand side of our equation is positive if y is between k and between 0 and k, so which means that the direction field looks like this. It is negative if y is bigger than k, and negative if y is smaller than 0. So now you can imagine that the asymptotic behavior is like this. So the exact terms for these two parameters are R is the intrinsic growth rate and K is the carrying capacity. So here you see the picture. So the intrinsic growth rate governs kind of steepness of the arrows, right? So the more, the higher, the bigger the intrinsic growth rate is, the faster the solutions grow in the beginning. Right? So which means that if the coefficient at y is large, it means that the arrows are kind of steep. If it is smaller, then the arrows are not so steep, but they're still positive. So the solutions are growing in this area between 0 and the carrying capacity. Yeah, and the carrying capacity is, so here it is 2, and here it is 1.4, so is an equilibrium solution. The logistic differential equation is a separable equation, and it is an autonomous differential equation. But again, since it is separable, it means that it is possible to solve it explicitly. It is possible to move everything with y to the left-hand side and everything with t to the right-hand side, and then solve it. So you can do it like this. You know, write dy over r. I mean, maybe not r. So r doesn't matter. R is a constant. Y times 1 minus y over k equals r t, and so on. It is a bit complicated, so I suggest that you try it yourselves, or you can just try this ready answer that some clever people have prepared for you and see if it fits into the differential equation.